So anyway, we'll pick up where we left off. We had last time we had Riemann, who did sort of double elliptic geometry. Right, so this is, or spherical geometry if you want to just call it that. They're not exactly the same thing, but spherical geometry is a model of double elliptic geometry, which is really just the geometry of a sphere. And the lines on a sphere are, of course, great circles. They are the intersections of planes that cut through the circle, or sorry, cut through the sphere, through the center of the sphere. All right, so along comes, this was 1850s, I believe it might have been 1850 on the dot. Along comes Klein, Felix Klein. Don't know exactly when he did this, but I know he's alive from about 1850 to 1925, I think. So probably I'd guess 1870s he might have introduced this stuff. This is single elliptic geometry. So the big problem with double elliptic geometry, and this is why it's double elliptic, is because any two lines always intersect at two distinct points. And that's a bit weird, right? We want lines to intersect at just a single point. So single elliptic geometry, he comes ahead and he fixes this. He says, all right, so I want lines to intersect at a single point. At a single point only. And since lines, which are of course great circles, always intersect at two antipodal points, since they always intersect at antipodal points, let's identify them. I.e., and what I mean by that is this is, I literally make them the same point. All right, so I don't know how much you've thought about identifying things in mathematics. I'm sure you've done it with equivalence classes and stuff, and you're familiar with this process. But let's talk about this topologically. So, can I erase this? Topological identification. Suppose I just take a point. I take a sheet of paper. All right, so we'll pretend this is finite. It's just a sheet of paper. And what I'm going to do is I'm going to identify every single point on this side with every single point on this side. So this point here, I'm going to topologically say that's the same as that point. Right? This point here, I'm going to say topologically that's going to be the same as that point. So even though on the board they look like different points, mathematically, abstractly, I'm going to say these are the same points. And for every single point on this side, I'm going to say they're the same as points on this side. So think of, if you want, what I'm really doing here is I'm taking this and I'm gluing it to this side. Right, so I take this sheet of paper and I say these points here are going to be the same as these points here. What do I get when I do that? Well, if I glue them together, I now have a topologically different surface. I now have a cylinder, right? So this turns into a, takes this thing and turns it into a cylinder. Because I sort of glue them together. What do you think you would get if I then said, all right, every single point on this side, I'm going to attach to, or identify with every single point on this side. So all of these points will be identified with all of these points. Maybe I should draw another picture. Oh, by the way, before I get into that, this that I've drawn right here, this sort of identification of identifying this side with this side, identifying this side with this side, that's literally Pac-Man, right? Pac-Man goes off this side of the screen, comes back on this side of the screen. So Pac-Man lives on a cylinder. Right? This is all that's happening. When he comes off here, he's actually over here because he lives on a cylinder. But suppose I identify this side and this side, and then this side and this side. So I make these edges the same as well. Topologically, what do you think this would turn into? So I glue these together to get a cylinder, and then I'm saying, all right, so these are the same as well. Yeah, you would get, you'd have your cylinder, and then these would have to reach around to become the same, so you get a torus or a donut, yeah. Where these ends sort of glue on some sort of circle. Just to make sure you're really getting this, once again, take our sheet of paper and we're just going to identify all boundary points. What would you get there? If I say all of those boundary points are literally the same point, what do you think this would look like? I just try to imagine it, right? I've got a sheet of paper and I say all of these side points, all the boundary points are kind of trying to become the same point, so I'm curling it up on itself. They're sort of all collapsing to a single point. This is basically topologically a sphere, you know? Or something of a spherical shape, right? Spheres have curvature and whatnot, but anything that looks sort of like a sphere could be elongated, but whatever. So this is mathematical identification, right? This is what identify means in math. It doesn't mean this sort of English of, I guess, look at something and determine what it is. Identifying things in mathematics means literally make them the same. And topologically, this has interesting ramifications. But here's what Klein did. So Klein looked at the sphere, right? He looked at the sphere and he said, all right, antipodal points. How about this point and its antipode on the back there, I'm going to say those are the same. And choose South Pole down here and the North Pole up here. Those 2 points are literally the same. And do that for all pairs of antipodal points. So when we identify all antipodal points, we obtain and unfortunately, think about what's going to happen here. This point would sort of glue to this point and become the same. This point would glue to this point and become the same. Unfortunately, we get a surface it's not going to embed in three-dimensional space. It actually lives, if you want to draw something that doesn't intersect itself all over the place, you'd need 4 dimensions to do it. So unfortunately, we obtain a surface that, there's a mathematical word for this, that does not embed in R3. This is akin to Pac-Man's world. Pac-Man's world doesn't embed in 2-dimensional space, right? Pac-Man actually lives on a 3-dimensional cylinder. Well, a cylinder that embeds in 3-dimensional space, but not 2. What we're doing here, this isn't going to embed in 3-dimensional space. You need 4 dimensions to really view it, but that's okay because it's still easy enough to visualize. Here's really what you get. You get an upper hemisphere. So the result is an upper hemisphere so all of these points on the upper hemisphere are unique points. They're all individual. None of them are identified together. Upper hemisphere where only the points, only the antipodal points on the equator are identified. All right, so what I mean by that is here's a point, P, that's the same as its antipodal point over there, P prime. All right, so every point on the strictly the upper half sphere, all of those are their own points, right? They're not identified with anything else in this result topologically. But the points on the equator are. They're still identified with their antipodal points. This is literally the same point as this point. What does that mean? That means if I'm walking along a line, if I start here and I walk along a line and I come around to this point, well, now I'm back over here again, right? So a couple of notes. What does this mean? Well, let's look at 2 lines. Here's another line, here's another great circle. Those are, of course, intersecting lines. How many points of intersection do those 2 lines have? right? Obviously they're not intersecting here, or here, or here, or here. They're just intersecting here, right? So how many points of intersection is that?
2.
These are the same point.
Oh, 1.
So just one. All right, that's why we identified them, because now lines intersect at just a single point. So lines intersect at a single point only, hence single elliptic geometry. Because we don't have this issue of having 2 poles anymore and lines, different lines passing through different poles, we now have this nice property that through any 2 points, there's a unique line. Through any 2 points, there is a unique line. Once again, we still have no parallel lines. Doesn't matter which lines you draw on here. You draw 2 lines, they're going to intersect. Right? Even these 2 that I tried really hard to not make them intersect, they still want to intersect along the equator. So there's no parallel lines. But there is something that this doesn't have that would have been kind of nice, which is, remember in double elliptic geometry, if I draw a great circle on here, this great circle sort of separates the sphere into 2 halves, right? This line, I'm either over here or I'm over here. So we still had the plane separation axiom in double elliptic geometry. Every line separates the entire space into 2 different sides. That's not true over here, right? Why? Well, suppose I'm standing here, right? Suppose I'm standing here on this side of this line. How can I get to this side of this line without crossing it? Well, I could walk to here. That teleports me over here, and now I'm on this side, right? So there is no plane separation axiom. Lines do not slice. They do not cut the space, the geometry into 2 different sides. So the plane separation axiom does not hold. And there's certain really important results here that that we're not going to have because we don't have the plane separation axiom. You might not remember this, but for example, the neutral result, the proof of the exterior angle theorem, that actually relied pretty solidly on the plane separation axiom. And it's not hard to see. You can draw a counterexample right now in either one of these models. Draw a counterexample of the exterior angle theorem. Well, what I want to do is prove some results. These won't be super formal proofs. I'm going to have to hand wave a few things because I'm not going to tell you exactly which neutral results are still true, exactly which aren't. But if you're ever iffy, if you're ever thinking about which neutral results are true and which aren't, just think about these spaces. To be honest, in my mind, I almost never think about this when I'm trying to come up with counterexamples. I still think as if I'm living on a sphere. Why? Well, because you can sort of almost always forget about the weird stuff happening here with these identified boundary points and just pretend when you're drawing triangles and stuff, pretend you just live up here where it's like living on a sphere, right? And yeah, if you're trying to think, is this result still true in elliptic geometry, it's pretty easy to think in terms of a spherical model and ask, can I find a counterexample or not? right? For example, suppose I put a triangle on here. Suppose I put a triangle on here. Do you think the crossbar theorem is still true? If I start drawing a ray this way, is it going to have to intersect this side? Seems pretty likely to me, right? So some things are still obviously true. But once again, the text isn't super formal with this. I won't be formal. We're not going to go through all of the neutral results. In fact, I haven't even told you precisely which postulates we still have. But we'll do what we can. And here's the first theorem. It's the polar property. And so it says this. It says if L is any line in elliptic geometry then there exists a point P such that every line connecting P to a point on L is perpendicular to L and P is equidistant. From all points on L. So this is named based on actual sort of the ideas from the North and South Pole, which is, think about the equator, but this is just one line, one great circle of many on a sphere. On the equator, there's a point P, which is, in this case, I'll draw the North Pole, is a point P, such that when I draw any line from P down to L, when I draw any line from P down to L, that's going to intersect it perpendicularly, right? And that distance from the equator to the North Pole is the same distance no matter which of these lines you walk along, right? So they're all the same length. So this point P is called the pole of L. And this distance from P to L is called the polar distance. Notice I haven't used a particular thing here that you would expect me to say. I haven't thrown in a few extra words. You might expect me to call this the polar distance for L. But again, it's not too hard to think about on a sphere. What if I had a different line and I thought about where the pole is relative to that line? Well, it wouldn't be too hard to convince yourself, at least just visually, that the polar distance for every line is exactly the same, right? If I have another line here, I'm not going to draw it, but if I attempted to put a pole on here, it'd be the same distance away. So this is the polar distance, and a fact or a theorem. I won't attempt to prove this at all, so I'll just call it a fact. The the polar distance is the same for every line. That's why I'm not saying polar distance for L, it's just the polar distance. Does this all make sense? Are you content with this? All right, so we have to prove that poles exist. Given a line, there's a pole, there's a point with this property. Every line to L is perpendicular, and they all have the same length. And this extra fact, this extra theorem, I won't prove it, but it's true. So every line has the same polar distance. You'll notice one more thing I've said is that there exists a point P. Again, it shouldn't be too hard to convince yourself that in double elliptic geometry, there's two poles, right? I've got the north and the south pole for this equator. So there's 2 points with this property. But in single elliptic geometry, poles are identified. So in single elliptic, there is in fact just a unique pole there because they're the same point. All right, so let's prove this. Again, the proof will be a little bit hand-wavy because I'm going to invoke things like the isosceles triangle theorem, which we don't know is true in elliptic, but it is. So let's let Q and R be any 2 points on a line. Well, 2 distinct points at least. 2 distinct points on L. And let's construct lines M and N perpendicular to L. Through Q and R respectively. So here I have L, here I have Q, here I have R, and I've got these 2 lines that I'm only going to draw just a little tiny bit of right now that are perpendicular to L. What do I know about M and N? Is it possible that they're parallel? No, right? No lines in elliptic geometry are parallel. So this is in fact we've taken this as sort of the elliptic parallel postulate, if you want. Given a line and a point not on that line, any line through that point must intersect the original. So I'll just say by the elliptic parallel postulate, if you want. By the elliptic parallel postulate, M and N must intersect at a point P. So these 2 lines through Q and R, they have to intersect at a point P. So now I want to prove that P is the pole. Well, in fact, before I do that, let's prove one more thing, which is that I want to prove that P is the same distance from Q as it is from R, and that follows by the isosceles triangle theorem, right? because this is an isosceles triangle, these two sides have the same length. Again, we haven't proven that this is true in elliptic, but trust me, it is. So because triangle PQR is isosceles, PQ is the same length as PR. And now this will take some convincing, but well, you have to think about it, I suppose. But there's one more thing I need to do, which, okay, so I've proven that P is the same distance from Q as it is from R. Both of these lines are right angles. But to be a pole, it has to be the same distance from every point on L. And when I draw the line from P to every point on L, I should get a right angle. So I'm just going to say that because Q and R are arbitrarily chosen, it suffices to show that that S, which is going to be the midpoint of Q and R, is also the same distance from P, and PS also intersects L orthogonally. Right, so show that S is also the same distance from P. What I mean by that is i.e. PS is equal to PR is equal to PQ. And that PS is perpendicular to L. Why does this suffice? Well, because Q and R are arbitrarily chosen. Every point on this line is the midpoint of some isosceles triangle. So as long as I can prove it's true for the midpoint of these isosceles triangles, you can choose Q and R arbitrarily and then prove it's true for S. And so this is really where I'm coming from here with this argument. And yeah, why are these true? Well, if this is the midpoint, then those two sides are the same length, right? So again, I haven't told you exactly which postulates we have in elliptic geometry, but in neutral you would say by SAS, these two triangles are congruent, right? And we do have SAS in elliptic, so by SAS, triangle PQS is congruent to triangle PRS. That implies that both of these angles here must be the same. If they're the same and they're linear, then they must both be right angles, right? So I'm just going to write immediately. We'll finish up this proof very quickly here. This implies that that angle QSP is equal to RSP, and they're both 90. Measure of angle QSP is equal equal to measure RSP, which is 90 degrees, which is what we wanted. And once again, that means, because these are isosceles triangles, that means that each side is the same length. So this is the same length as this, is the same length as this. So which implies that triangle PQS and triangle PRS are isosceles, which implies that PS is equal to PR is equal to PQ. Done. And again, a bit of a hand-wavy proof, but most of this is just using neutral results with this one extra postulate that we haven't usually used, which is the fact that if I have two lines, those two lines have to intersect. They have to. Even though the alternate interior angle theorem from neutral would say, hold on, these are parallel, because we're in elliptic geometry, we don't have the alternate interior angle theorem, and they have to intersect. And if that happens, you can prove all sorts of interesting results. But there's the big one. This is the most important one. Just about everything you prove stems from this polar property. And from here we probably, I guess, just have time to prove one more thing. So here's our next big theorem about triangles. In any right triangle of elliptic geometry, each of the other two angles has a measure less than, equal to, or greater than 90 degrees, dependent on whether, on whether the side opposite the angle the side opposite it has a measure that is less than, equal to, or greater than the polar distance. Right, so if you think about what's happening here, this is kind of obvious. Once again, imagine you're living on a sphere, right? Or, yeah, let's pretend we're in double elliptic geometry here. Here's a portion of a right angle, or a right triangle. So here's the North Pole, here's the equator, and here's a right angle. So we'll call this A, then I'll come over here. Our next line segment will live along the equator. There's B. And here's our pole P. So what happens if I just connect these? Well, this angle would be a right angle, right? Because there's the pole. So if the side opposite this angle B, if that side has length that's equal to the polar distance, I get a right angle. Agreed? Now if I take the side length to be less than the polar distance, if I take this side to be less than the polar distance, there's C, well then I get an angle that's acute. I get something less than 90 degrees, right? And if I were to take this side length to be bigger than the polar distance, I put C over there, and now I get some sort of triangle like this. Well, now this angle is bigger than 90 degrees. So this is the observation that this theorem is making, and it's a really important observation when you're proving things, is if I have a right triangle, and I know that one side is either less than the polar distance, equal to, or greater than, then I can tell you whether this angle that's opposite that side is acute, right, or obtuse. We only have 5 minutes, but I think we can prove this very quickly. It's really just making these observations. So the triangle ABC be such that measure of angle C is 90 degrees. So here I have my triangle C, A, B. Because this is a right angle, where's the pole of side AC? The pole of side, or length side, what am I saying, not side, line AC must lie somewhere on BC. Right, because this is a right angle, the pole is somewhere along this line. So there's the pole P. So the pole P of line AC must lie on this ray CB, because CB is perpendicular to AB. And because P is the pole of AC, I know that this angle here is a right angle. The measure of angle PAC is 90 degrees. Sorry, I'm moving fairly quickly here because we're just about out of time, but is everything okay so far? All right, because this is a right angle, the pole is somewhere along this ray CB. And wherever it is, when I construct this angle from the pole to A to C, because it's the pole for this line, that angle must be a right angle. All right, now there's three possible cases. If B is equal to P, well then the measure of angle BAC the measure of angle PAC, which is 90 degrees. So just as we wanted, if this side length is equal to the polar distance, then this angle here is a right angle. If I have the instance that's drawn in this picture, if P is between B and C, so if B, then P, then C, so BP, oops, so BC is greater than PC. I.e., this side is longer than the polar distance, then as shown in the picture, this angle here is bigger than 90 degrees, right? Because it's got a 90-degree interior angle. So then, measure of angle BAC is bigger than 90 degrees, as shown. And 3, the instance I haven't drawn, but if P, then B, then C, so BC is less than PC. All right, so if P lies somewhere way out here, well then this is the right angle, right? And this angle, BAC lives inside of that, must be less than 90 degrees. All right, so then measure of angle BAC is less than 90. So I hope to get just one result a little bit further, talking about security quadrilaterals, but I guess we'll do it next time. So we'll stop here. But this is a really, really important result. If you have a right triangle and you know something about the angles or something about the side lengths, then you can say something about the other and vice versa. But I don't want to prove formally too much stuff in this section. We'll go through some of the results next time, I guess, without proving them. But essentially, in a nutshell, anytime in Euclidean geometry, we did all these results involving equality, right? We had triangle sums are equal to 180. Meanwhile, in hyperbolic geometry, we had less than or equals, or so strictly less than 180. In elliptic geometry, you always have the third possible case. You have that angle sums are now bigger than 180. So anytime you have equality in Euclidean, less than in hyperbolic, the elliptic result is greater than. And there's lots of cases of this. We'll go through it next time. See ya.